In this video, we're looking at section 7.3, which is called least squares approximation. And let's talk about the big idea we're going to be looking at in this section. So remember that when you have a system of equations like ax equal b, that system may be inconsistent, meaning that system might have no solution. And what we want to talk about in this section is how to find the best possible solution to a system that is not actually solvable. So towards that end, let's look at a first definition here. Let's say that we're given an approximate solution to the system, and we'll call that vector S. We're going to introduce what's called the error vector, and the error vector is going to be the vector b minus as. So let's think about why that would make sense. So if you had an approximate solution to the system, instead of saying ax equal b, you'd be instead replacing that x with an s, and you'd say as is going to be approximately b. So we can get a sense of how good that approximation is just by subtracting as from the right side here. We'd have b minus as. And essentially, the closer that vector is to the zero vector, the better our approximation is going to be. So that's the error vector, which is showing the error in the different components of the vector. And if we wanted to boil that down to a single number, we could talk about the error just by calculating the length of that vector b minus as. So the smaller that length is, the better the solution S approximates solution to the system, or the better the solution S is, you could say. All right, so with that, we're going to look at a second definition here. The least squares solution, which in symbols we're going to write x star because it's a special solution. The least squares solution is the approximate solution with the smallest error. So it is the best possible solution to the system, given that the system is not actually solvable. And here's the formula that we're going to be using to find this least squares solution. We're actually going to derive the formula at the end of this video, but for now we'll just practice on using the formula and make sure that we understand conceptually what's happening. Okay, so the formula is x star is going to be A transpose A, all inverted, times A transpose B. So notice that the only two things that that formula depends on are just the matrix A and the vector of constants B. All right, so with that, let's try a first example. So here we've got a system which is inconsistent, and we are going to find the least squares solution, x star. Okay, so we would start by calculating A transpose A. So A transpose, just turn the columns of A into rows. So there we go. And we're going to multiply that by the original matrix A. There it is. Do our usual matrix multiplication. We get 2, 1, 1, 2. And then our next task is to take the inverse of this matrix. So just using the formula for a 2 by 2 inverse, we should first calculate the determinant. 4 minus 1 is 3. So we're going to go 1 over 3, swap the diagonal entries, and change the sign of the off diagonals. Okay, there's our inverse. And now we're ready to write down x star, our least squares solution. So we're going to take this matrix that we've just calculated. We're going to multiply that by A transpose and then times B. So A transpose being 1, 0, 1, 0, 1, 1, and B being the vector of constants from the right side of the system, so the 1, 2, 6. Okay, if you like, I could have written a step in here just to write out the general formula so we're comfortable with that. So let's do that. So x star in general, the inverse of A transpose A times A transpose B. So that's what we're doing here, calculating that x star. Okay, so let's multiply the last two matrices here together. We'd keep our matrix in front the same, and multiplying through here, the 101, 0, 1, 1 times that vector of constants, that's going to give us 7, 8. Okay, so we'll keep our 1/3 in front, and now we're going to multiply the 2 by 2 matrix times the 7, 8. So that's going to give us 6, 9, and if we like, we can divide both those constants through by the 3. So 2, 3 is our least squares solution. So that's our first example of actually finding the least squares solution. Now I wanted to do a follow-up here and just make sure we understand conceptually what's happening when we calculate that least squares solution. So remember, we defined the error vector to be b minus ax. So for this example, b was 1, 2, 6, and our matrix A was 101, 0, 1, 1, and we're going to multiply that by, in fact, I should have written ax star here. I'll just highlight that. So our error vector is b minus ax star in this case where we're working with the least squares solution. So we're going to multiply our matrix A with this x star that we've just calculated. And roughly that's telling us, in terms of a vector, what kind of errors we have in each of the components when we use x star to solve the system. Okay, so let's see what this looks like. We'd have our 1, 2, 6 minus 2, 3, 5. And so the errors that we're getting in the various components, -1, -1, and 1. All right, now if we wanted to boil that down to a single number, then we would call that the error, and we would get that error just by calculating the length of this vector here. So we'd say the error is √3 for the least squares solution. So what that's telling us is that every other vector x that we could think about putting into this system and testing, how close ax comes to equaling b, for every other x, let's say every other x has error bigger than √3. So you can try any other vector that you like in R2. You can put anything, any real number into either of those components, calculate the error for that particular vector, guaranteed it's going to be √3. So that's what we mean when we say that the vector 2, 3 that we found up here is the best possible solution, or formally the least squares solution to the system. Okay, let's do a couple of quick examples now. We'll see how this might relate to something that you would see in stats, or maybe in chemistry, or maybe some of your other courses. Very common to ask for the best fit line through a data set. So imagine that someone gave you a set of XY coordinates, and we're going to try to find the best fit line. In symbols, we'll say y equals a0 plus a1x. Okay, so key thing to realize here is just what our variables are. A0 and A1 are the unknowns, which is a little unusual, right? Usually we're used to thinking of x and y as being our variables, but in this case it's actually the A0 and the A1 that we're trying to find, because we're given the values of x and y in the problem. So that requires a little bit of a mental shift. That means that we're going to take this equation here and we're going to write it slightly differently. First of all, we're used to seeing variables on the left side of the equation. So we'd write a0 plus a1x equals y, just to get the variables on the left side. And the other thing that we're used to is we usually write a coefficient before our variables. So we're used to writing something like 2 times x. Pretty weird to write something like x times 2. So we should actually write this as 1 times a0 plus we should write x times a1, because a0 and a1 are the variables, whereas 1 and x are actually going to be the coefficients. Okay, and then that prompts us how to set up our system. So the idea is that the a0 and the a1 are the variables, so they're going to go into this position here. And what we need to have in the columns are 1 and x. Remember that when we do a multiplication, we're multiplying that row with that column there, so we actually need the 1 to multiply with the a0 and the x to multiply with the a1. So that's why we set it up that way. Okay. Okay, and then on the right side, we're just going to have our y values. So let's fill in the numbers here and just see if we can figure out what this matrix needs to look like. So when we say that we have ones in the first column, it means just write 1, 1 like that in that first column. In the second column, oh, in fact, we have 3 data points in this problem, so we're actually going to see 3 different rows in that matrix. So if you had, say, 10 data points, you'd have 10 different rows in this matrix. 20 data points, you'd have 20 different rows, but you would only ever have 2 columns there. And similarly, on the right side, you'd have a number of rows equal to however many data points you have. In this case, it's 3. Okay, so we need to write 1, 1, 1. And then we'll fill in our x values, so 0, 1, and 2. And then on the right side, putting in the y values that were given in the question. So there we go. That's the system that we need to solve to find the best fit line. So we did a calculation just like this a moment ago. This is going to be our matrix A. That's going to be our set of constants B. And you could calculate the least squares solution just by going through the process A transpose A inverse times A transpose B. I'm going to say dot, dot, dot. If you're really into this, you can go through and just check what it comes out to, or you can trust me either way. So it comes out to 11/3 and -2. Okay, so when we go through this calculation, we find the least squares solution. What we're actually finding is the A0, A1 that gives us the best fit line. So you can call this X star, but maybe better, more descriptive to call it A0, A1 at the end of the problem. So let's see how that helps us answer the question. Remember that our best fit line was written in the form y equals A0 plus A1x. So we can now write down our best fit line. So y is going to be 11/3 minus 2x. So that is the best fit line through our data set, and this process would work for any problem that has this kind of setup. Okay, now next you might be wondering, what happens if I need to fit a higher degree polynomial through my data set? Maybe I've got some parabolic data, I want to find the best fit parabola through a data set. So I'll show you how to modify this, really just a minor modification. So we'll do another quick example here. Let's find the best fit parabola through this data set. Okay, so let's say that our best fit parabola looks something like y equals A0 plus A1x plus A2x squared. So the unknowns in this problem are these A0, A1, A2. The x and y values are given in our data set. So again, this is always a bit of a mental shift when we're doing best fit curves. Is just that our variables actually turn out to be these coefficients that we're trying to solve for. Okay, so if we write our equation in a more descriptive way, we would put our variables over on the left side, like that. And we would also put coefficients in front of variables. So we'd say 1 times A0 plus x times A1 plus x squared times A2. And that's going to prompt us how to set up our matrix. So the idea is when we go and transform this into a system, our unknowns are going to be the A0, A1, A2 here. And let's think about what has to multiply with what. So we want 1 to multiply with A0. We want x to multiply with A1, and we want x squared to multiply with the A2. So if I just erase all these kind of lines here, that's going to describe to us how to fill in the different columns of this matrix. And then on the right side, we're going to have our y values. Okay, now the number of rows is just going to depend on how many data points you have in your data set. In this case, it's 4, so we're going to have 4 rows in this matrix. So we'll have 1, 1, 1, 1, like that. Second column is just going to contain our x values from our data set, so 1, 2, 3, 4. And in the third column, we're putting the squares of the x values. So just look at each x value and then square it to get the next value. So 2 squared is 4, 3 squared is 9, and 4 squared 16. Okay, so that's how we get all those numbers in the x squared column, just the square of the appropriate x value for that row. And then over on the right side, y values, 1, -2, 3, 4. Okay, so this is our matrix A. This is our matrix B. And in a similar way to our previous two problems, we are going to find the least squares solution by going A transpose A, inverting that, and then going A transpose B. So what's interesting about this problem is that A transpose A will be a 3 by 3 matrix. So it makes the calculation just slightly trickier here. You could use a few different methods for finding the inverse of A transpose A. You could use the Gauss-Jordan method. That would probably be my go-to method of just putting the matrix in on the left and the identity matrix on the right and trying to reduce that to find your inverse. There are other things you could do. You could use the adjoint formula for the inverse if you remember that, or you could use software, just any online software to find the inverse as well. So the number of data points in your data set is actually irrelevant to the size of the matrix. What determines the size of the matrix is really just the degree of the polynomial. So if you were trying to fit a third degree polynomial through your data set, you'd have a 4 by 4 matrix. In general, nth degree polynomial through your data set, n+1 by n+1 matrix that you're dealing with. All right, so if you went through all the details, if you were really interested here, you would find that x star comes out to 3 minus 18 over 5 and 1. And what that x star represents in order are the values of A0, A1, and A2. So if we call our best fit parabola y equals A0 plus A1x plus A2x squared, then our best fit parabola is y equal 3 minus 18/5 x plus x squared. Best fit parabola through that particular data set. So we're going to do one more example along these lines of finding the best fit curve. For our next example, we're going to find the best fit exponential curve through a set of data. Okay, so we're given some t values and some p values. And what we're trying to do is find a curve in the form p equals c e to the kt. So in other words, the unknowns that we're thinking about here, the c and the k are what we're trying to find. Okay, now before we get too far ahead of ourselves, basically what we need to do is transform this equation here into something that looks like a linear equation so that we can use linear algebra. So the key insight is to take ln of both sides. We could say ln of p is equal to ln of c e to the kt. So ln of p is equal to, well, when you have ln of a product, that turns into a sum of lns. So ln c plus ln of e to the kt. And then because ln and exponential are inverse functions, we just get kt there. Okay, so the variables, or the unknowns, are actually going to be ln c, that's one of our unknowns that we're going to figure out, and k. So ln c and k are the values that we're going to solve for. The idea is that once we found the value of ln c, we should be able to actually get the value of c from that pretty quickly. So let's write this equation more suggestively. We'll write variables on the left. So ln c plus kt equals ln p. And the other thing we want to do is just put coefficients in front of the variables. So we should write 1 times ln c, and instead of writing kt, let's write tk. So that's going to prompt us to set up a system that looks like this. So the unknowns will be the ln C and the K. And let's think about, as we do a matrix multiplication, what's going to multiply with what? Well, the 1 is going to multiply with the ln C, and the T is going to multiply with the K. Okay, so that means that we need to have 1 and T in the columns here, and then over on the right side we would have ln P. And then number of rows in the matrix will just depend on how many data points you have. So we've got 3 data points. We're going to write just 1, 1, 1 along that first column there. In the second column, put in your T values. And on the right side here, ln of P. So we're literally just going to write things like ln 5, ln 8, ln 12. Best to keep this all exact until the end of the problem. All right, so this is our matrix A. That's our matrix B. And we're going to do our usual least squares solution calculation. So we need A transpose A, all inverted, times A transpose B. So let's go for it. Start off calculating A transpose A. So 1, 1, 1, 0, 1, 3 times our original matrix A. It's going to give us a nice 2 by 2 matrix here. So 3, 4, 4, 10 is our A transpose A. And to take the inverse of that, we will just use the formula for 2 by 2 inverse. So our determinant is 14. We're going to go 1 over 14 times, swap the diagonal entries, and change the sign of the off diagonal. Okay, so now we can say X star is going to be this inverse matrix times a couple more things. It has to get multiplied by A transpose, and then it has to get multiplied by B. So I'm just referring to this formula up here to build the X star. All right, so A transpose has 1, 1, 1, 0, 1, 3 in its rows, and then our matrix B were the constants from the right side of our system. So the ln 5, ln 8, and ln 12. Great, so we'll do a little bit of algebra here. We'll do some matrix multiplication, and we will work out our X star, our least squares solution vector. I would say, just to avoid writing down a ton of lns in this calculation, it might be good to multiply these two matrices together first. So we'll go 1 over 14. We're going to create a 2 by 3 matrix, and then that's going to be multiplied by our vector of lns here. All right, so doing our multiplication, we're going to have 10, 6, -2, -4, -1, and 5, just from multiplying out those two matrices. And then we've got our vector of lns at the back here. So the ln 5, ln 8, ln 12. Let's do one more step of matrix multiplication here. I'm going to take each row and multiply it with that column there. So we're going to get things like 10 ln 5 plus 6 ln 8 minus 2 ln 12. So that is one number that's going in the top row. And in the bottom row, minus 4 ln 5 minus ln 8 plus 5 ln 12. Ln 12, there we go, 5 ln 12. Okay, so that is just a 2 by 1 matrix, just a single vector there that contains two numbers. And we might as well just round this off here so that we can talk about that in a lot more detail. So I'm going to give my answers just to 1 sig fig, but just for the sake of writing down the answer, let's write a few decimal places. So this comes out to about 1.686, and that one is like 0.279 approximately. And on the left side here, let's write down what variables these are. So if we scroll back to earlier in the problem, We had that discussion, but the variables in order, we can see them here in this equation, ln c and k in that order. Or actually, it was here that I wrote it down. So ln c and k in that order. Okay, so we're saying ln c is about 1.686 and k is about 0.279. Okay, so for the k value, that's great. We can say k is just approximately 0.3. If ln c is about 1.686, then that means c is about e to the 1.686. And if we do that to just one sig fig, it's around 5. So k value about 0.3 and c value about 5. So remember that our original equation from the question had the form p equals c e to the kt. So our best fit exponential curve through that data set, p equals 5 e to the 0.3 t. So that's how you can use the methods from linear algebra to solve any system that's inconsistent. You can find the least squares solution. You can, in particular, find the best fit polynomial through any data set, or even the best fit exponential curve through your data set. So really useful to a wide variety of different contexts. So the last thing we're going to do in this video, and in fact the last thing we're going to do in the entire course, is look at the derivation of x star. So it's pretty short. You can probably do it in under 10 minutes, but it's really going to tie together a lot of the big ideas in this course. We're going to look at this derivation and we're going to understand things like, why did we need to talk about column space? Why did we need to talk about projections and orthogonality and null spaces? So all of these big ideas are going to come together and help us to understand this single formula about how we find the least squares solution. So let's call this the derivation of x star. And we're going to start with a fact from chapter 2 that says that a system ax equal b is consistent if and only if b is in the column space of A. So let's consider an inconsistent system. That's what we're doing in this context here. So we're trying to find the best solution to a system that's unsolvable. And so if our system is inconsistent, that means that B is not in the column space of A. So in our picture here, we can say, let's just imagine geometrically that column space of A is, say, a plane through the origin, maybe in R3. And so the point is that the vector B is not in that plane. So we'll draw B coming up out of that plane. Now let's see what happens if we actually project B onto the column space of A. So take this vector B here, which is not in the column space, but project it onto the column space. So just project it onto that plane there. And what that's going to give us is AX star. Because conceptually what this vector is it's saying, well, we're getting as close as possible to B as we can get while still staying in the column space of A. The column space of A is exactly the set of vectors that look like A times something. And if this vector is as close as possible to B, then the correct name to give it would be AX star, because the least squares solution is that vector that gets us as close as possible to B when we multiply it with A. So I should actually write A times vector X star there. Okay, so AX star, projection onto the column space of B. So what would be interesting then is if we think about this vector that's coming up vertically like this. That will be our next conceptual step, to think about that vector there. So let's look at another picture here. So this vector that's coming up vertically, this guy right here, is going to be orthogonal to the column space of A, because what we're really doing in this picture is we're decomposing the vector B into something that is in column space of A plus something that is in the perp of column space of A. So we're doing an orthogonal decomposition of this vector B. All right, so this vector coming up vertically is perpendicular or orthogonal to our column space. And if we think about the right name to give to this vector, it would just be B minus AX star. Because you can think geometrically, how would you build that vector? Well, you'd have to go backwards along this guy and then forwards along that guy. So that would be B minus AX star. Therefore, we can say B minus AX star is orthogonal to column space of A. Great. Okay, now let's bring in a big idea from section 5.2. If we wanted to be really fancy, we could say B minus AX star is in the perp of the column space of A. Because what is the perp of column space of A? Well, it's just the set of vectors that are orthogonal to column space of A. So that would be a fancier way of saying that idea. You could even take this a little bit further and you could say B minus AX star is in the null space of A transpose. Oh, so I actually already had that written down. So B minus AX star is in the null space of A transpose. So you might be wondering why. This goes back also to section 5.2. We said that anytime you're looking at the perp of the column space for any matrix, that's always going to equal the null space of the transpose of that matrix. So if you're not sure about that, probably the best way to understand that is just to go back to section 5.2 and see an example that we did of that. But that's going to be really helpful for us because the null space of A transpose is now the idea that's going to allow us to move into an equation. Because right now we're just talking about a vector and we're saying this vector lies in a certain subspace. Okay, great, that doesn't give us an equation, but if we consider the perp of the column space of A as the null space of A transpose, this is quickly going to give us an equation. Okay, so let's remember what null space means. So I'm just going to do this as an aside. If you say null space of a matrix B, for example, you're talking about the set of vectors X so that Bx equals the zero vector. So null space is the set of vectors X that multiply with whatever matrix you've got to give you the zero vector. Okay, so if we say that this vector B minus AX star is in the null space of A transpose, then we're saying when we take A transpose and we multiply it with this vector, B minus AX star, we get the zero vector. So this is making me really happy. This is our first actual equation involving X star, and this is exactly what we're going to use to get our formula for the least squares solution. So let's expand this out. A transpose B minus A transpose A X star equals a zero vector. Let's bring one of the terms over to the other side. A transpose B equals A transpose A X star. Often we write this the other way around. So A transpose A X star equals A transpose B. When you write it like this is actually called the normal equations. That's just the fancy name for that particular equation. So you might see that name in your suggested homework. Normal equations just refers to this equation here. And if you wanted to really solve for X star, we could do that in the next step. So the idea would be just to apply the inverse of this matrix here to both sides. So if we apply the inverse of that matrix to the left side, that matrix will just go away from the left side. We'll have our X star. And on the right side, we would have that inverse matrix coming in on the left. So we'd have A transpose A all inverted times A transpose B. And that gives us the formula for the least squares solution. So I think it is incredibly cool that linear algebra is actually the subject that contains all the theory you need to do things like find the best fit curve, not just the best fit line, but any higher degree polynomial, even things like exponential curves through your data set. So incredibly useful because linear algebra is an incredibly powerful subject. So I'm glad I could share some of these big ideas in linear algebra with you. This is actually the end of our linear algebra course. So congratulations for making it this far. Thanks for watching.